In our first lecture, the topic of control is introduced with a closed-loop control system, i.e., a system regulated by a feedback loop, as shown to the right. Here, the red box represents the regulated system, and the green box represents the feedback, which is often referred to as the control law. From this perspective, the overarching goal is to design a control law describing the structure of the generating feedback that achieves a desired objective, such as driving a robot towards a prescribed location, maintaining an airplane's altitude under turbulent conditions, or minimizing regret associated with the actions taken by an autonomous agent. For dynamical systems, i.e. system parameters theta change with time, adaptive control methods give the control law flexibility in modifying its action to achieve its objective. When the objective can be formulated as a differentiable cost function, J mapping elements from RD to R, extremum seeking control is an effective adaptive control strategy that can track local minima or maxima of J with guaranteed convergence and stability under a set of well-defined conditions. Here, we see the general n-dimensional extremum seeking control scheme where red and green boxes again illustrate system and feedback, respectively. Note, this representation differs from the extremum seeking control scheme introduced in lecture 4.2, where measurable system output f of theta is now formulated into a cost function j of f of theta. Theta is not restricted to r, and sinusoidal inputs shown by a B sign and A sign are now fully parameterized. For this presentation, we also remind ourselves that the black boxes labeled high pass filter, integrator, and gain are transfer functions, which for continuous time systems allow us to convert input signals to output signals using simple multiplication in the Laplace frequency domain S. Unless explicitly stated otherwise, all presented functions are in the time domain. Note, extremum seeking control also works in discrete time. For the general extremum seeking control scheme, we define the necessary notation. System input is n-dimensional, where we have theta 1 to theta n in Rn. The model of the system F maps elements in Rn to Rd, which in turn get mapped to R via J. H is the high pass filter frequency, where signals with a frequency higher than H pass through the filter, and signals with frequencies lower than H are attenuated. Rho is an approximately zero mean oscillatory signal, since the high pass filter removes the desync component, i.e. mean value, from J of f of theta. Z sub I is referred to as the demodulated signal and measures gradients in J by way of its sign. K sub I is integral gain. Omega sub I is perturbation frequency. Phi sub I is phase shift, and theta hat sub I is the estimate of the input and is updated via integration of the demodulated signal with gain. A motivating example is used to illustrate the design of the extremum seeking control law, where a known static, i.e. does not change in time, convex cost function J from R to R of the form shown in the caption is considered. By injecting an additive sinusoidal perturbation, shown in purple, we'll just note here this purple signal is B sign, so we inject this sinusoidal perturbation to our estimate of theta. We add it, so it's an additive perturbation that gets then passed through the system. If we were to evaluate this into our cost function, this would actually produce a sinusoidal output as well. So as this value increases, we get an increase in J, and as this value decreases, we get a decrease in J. Okay? And this actually gets reflected in the green signal here, which is rho. The value of rho is the high pass filtered equivalent of J. Right? So again, the additive signal B sign, as it increases, J increases. As it decreases, J decreases. And this signal essentially represents J just with zero mean. Note that for this particular example, and for most extremum seeking control schemes with no to minimal noise, rho, the green signal, and A sign, the red signal, remain in phase for phi 0. So having passed a sinusoidal perturbation, the purple signal, we add it to our estimate that gets passed through the system. It gets evaluated at J, which produces a sinusoidal output. We then high pass filter that signal to give our green signal, which is zero mean. And if we were to multiply that green signal by a sine, the red signal, then we get the idea of Z, right? This blue signal. So the multiplication of both signals gives Z, blue, which is mostly positive. As you can see here, positive times positive is positive, negative times negative is a positive, to the left of J star, theta star, J star being the optimal value of J, theta star being the value of theta at which J star occurs. And if we were to look at this system over here where we have our purple perturbing signal, if we were to evaluate this at J, an increase in theta gives a decrease in J. That's why we have a negative rho, and then a decrease will bring the value of J actually higher. So if we were to multiply rho to the right by a sine, which again stays the same regardless of which side theta hat is on, we get a negative Z, okay? Positive Z to the left, negative Z to the right. Integration of Z into theta hat then drives theta hat towards theta star, okay? Where the integration of Z with gain is positive in the time domain and increases theta hat when theta hat is less than theta star. So again, you're integrating this value, which is positive, and you drive theta towards theta star. You're integrating this negative value when theta hat is greater than theta star, and it brings it back to theta star. Okay, and this is all dictated by Z, which again is found by multiplication of the high pass filtered cost function, which is rho, by this sinusoidal perturbation, which is multiplied to rho. Okay, interestingly, so when we have theta hat equal to theta star, this purple signal continues to perturb the system, moving theta hat away from its optimal value, with rho being mostly negative just to the left, or excuse me, rho being mostly negative actually on both sides because J decreases on both sides of J star. So you can see that if we were to increase theta hat by this amount, J is decreasing, so therefore the high pass filtered frequency would actually show a decrease. If we were to show this purple signal, which is decreasing theta hat, evaluating it in J, we would actually have a decreasing value from where it is, and this would also give a negative. So the interesting thing is when you multiply this rho by a sine, you get this sinusoidal function here, where as you approach theta star from the left, just as you hit it, this negative will actually drive theta star, or excuse me, theta hat away. And then this positive signal, when you're actually to the left, will drive it back. So you have this oscillatory behavior where you have increasing, decreasing, increasing, decreasing. And similarly for here, this Z, when integrated into theta hat, drives the value to J star. And then when you're just at J star, this positive value pushes it back. So again, you have this oscillating behavior. And depending on the direction in which you approach J, you can actually see that you'll have convergence onto J star that is sinusoidal just outside of its optimum, regardless of which side you look at. Okay, and then in the next example, we'll see this leads to persistent oscillations in theta hat. For the parameters listed in the heading, the middle figure illustrates convergence and stability results for theta hat and J, respectively, for initial input of theta hat equals 0. Note that theta hat practically converges to theta star around approximately 7 seconds and stays well within a 1 over omega squared neighborhood, approximately, right, on the order of theta star as t goes to infinity, and is practically illustrated for t going from 999 seconds to 1,000 seconds, right? So this illustrates practically t to infinity. For this example, theta hat may be initialized from any point in the domain of theta, and the convergence and stability results for t to infinity would be observed as there is a single global extremum. So regardless of the initial input of our theta hat, we could have initialized it from, let's say, 2, 3, 4, even on the opposite side of 6, we would actually have this signal actually converging still back onto 5, because there's a single global extremum, right? There's no chance of this getting caught in a local extremum off of the global. So also for J, we see J converges to a 0.04 neighborhood of J star. Again, this behavior is a result of Z, right? We get driven towards J star, and then just as we hit J star, we get driven back. And this creates this oscillating behavior as we are approaching J star from the left, right? If we were to go again from 0, the optimal value is 25 occurring at 5. Therefore, approaching from the left, we have this integration of Z with gain, giving this sinusoidal signal. We reach 25, but we can never exceed it. We actually get returned back. We have this oscillation about J star. Departing from the general scheme, Schenker and Krisick, who are the authors of the paper reviewed in this presentation, develop a novel extremum-seeking control scheme shown to the right, where J is combined within the argument of sine and cosine functions. This scheme is developed to address the uncertainty of convergence rate theta dot and control effort U that remains in all other extremum-seeking schemes as J enters the feedback loop in a defined way. Here, we see a representation of an input-defined system, X dot, where F and G sub I are smooth functions. In the author scheme, the system dynamics theta dot, which is equal to the actuating force to the system UI, formulates the sine and cosine functions, which are then multiplied by the square root of alpha sub I and omega sub I. Again, here, this alpha sub I is simply a scalar. So typically we have most control, extremum-seeking control schemes have this input-affine form where the controller will enter the system by a multiplication of a smooth G function, but instead now we have this cos function J gets formulated into the argument of a cos sine function, and that's the key novelty here. Interestingly enough, though the structure of the control law as well as the representation of the system dynamics is far different from the general scheme, it still behaves as an extremum-seeking controller. So if I were to re-implement this controller for the motivating example, you would actually see very similar convergence properties for theta. With this novel formulation, the following main outcomes are established in the main paper. So outcome number 1, control effort UI has guaranteed bounds of the square root of alpha sub I omega I. Okay, and then one can see that this result is trivial as the value of cosine is always bounded from -1 to 1 for any argument. So of course, if we were to multiply the cosine function containing J by this scalar quantity, you would then have U bounded by those scalars. Outcome number 2. So from the averaging results of Kurzweil and Yarnik and Sussman and Liu, the authors prove that the closed loop system on average satisfies the dynamics shown here, where we have theta bar dot sub I, right? And this can be solved, as you can imagine, as an ordinary differential equation. And that's actually a first order linear differential equation. If we were to move this to the left-hand side and we have the right-hand side then equaling 0, you can solve that ODE to determine the average trajectory of the system. Okay, now what is average? We recall from lecture 4 the notion of average by taking the limit as t goes to infinity of the integral of the function we are averaging, right? So for this particular case, we are averaging the partial derivative of our cost function j with respect to each theta I from 0 to big T. And then we consider this limit also 1 over t as well. Okay. Now, outcome 3. From the semi-global practical stability results of Morrow and Ailes, specific stability guarantees on theta star are made. At a high level, we generally consider theta star to be time varying. And we also consider theta to be initialized at time 0 with some value in its domain. So we have t and the x-axis, and we have our thetas over here. This theta star, you can imagine, changes in time. So this optimal value, we can actually track it in time. We know that at a particular time, it'll have a particular value. We then initialize, let's just say we have a simple system going from R to R. We can initialize theta wherever we want in its domain here, right? And then the authors prove that for an arbitrarily large set of initial conditions, the trajectories theta, which also just so happen to be a function of t, of the system theta dot converge uniformly, right? So these trajectories eventually, as t goes to infinity, converge uniformly to an arbitrarily small residual of delta, right? And this is set around theta star. Okay, this occurs when j has a unique global extremum and when 1 over omega is sufficiently small. Illustrating the convergence and stability results from the previous slide, the 2D vehicle control example from the original paper is re-implemented. In this example, the controller developed is of the form shown to the left, where controller U defines vehicle velocity as a function of heading actuation phi of t, where phi naught is an arbitrary initial vehicle orientation. Note this controller models unicycle motion, as shown in this diagram, which is unique for the author's scheme, as the general scheme presented earlier cannot accomplish this. The system state theta represents xy vehicle position, and the cost function j consequently is too a function of vehicle position mapping elements from R2 to R. Assuming j has stationary extremum, i.e. x star, y star does not move in time, the resulting closed loop system on average satisfies the dynamics stated in outcome 2 from the slide earlier. By simply changing cos to sine here for the second component of u, which is y dot, the stability results for theta star are slightly relaxed, though in simulation it is shown that the trajectory xy of the system still uniformly converges to the average trajectory x bar, y bar of the system. For the hyperparameters, cost function, stationary extremum, and initial conditions shown, the figure to the right illustrates convergence of trajectory xy, right? So for initially, we'll consider this black line representing the trajectory of the system towards the average trajectory. This average trajectory is the dashed black line. Again, we have x bar, y bar, giving the notion of an average, right? And again, this average trajectory is obtained by solving for this ordinary differential equation. So if I were to plug in j, take the partial derivative with respect to x, with respect to y, and use the average system dynamics presented in outcome 2, you would actually arrive at these dynamics for each of these components, which is as simple as an ODE you can get. And then the solution would actually give x bar and y bar, and that's illustrated in this figure. And it's simply a straight line if you're to plot x and y as shown. So in the bottom right corner of the figure here, we also see we have stability results for X star and Y star. X star and Y star occur at 0, right? If you can imagine taking or plotting this in 3D, you would see that the extremum is global and it occurs for X0, Y0. The solid black line here is within a constant residual around the optimal point. But if we were to add noise to the measurable output of the cost function, then the residual increases with increasing noise. This noise, we have two cases. We have case 1, which is red, and case 2, which is green. Case 1 has a larger noise than for green. And the green is set around a slightly larger residual than the black. And then for red, we can see that an increase in the order of magnitude of noise leads to a substantially greater neighborhood around which stability is achieved here, right? So this system does converge, but not uniformly. So under a sensitivity of 0 mean process noise xn, right? So the base case, we consider there to be no noise, added to the measurable output of J, the extremum seeking control scheme is sufficiently robust, maintaining a convergence along a gradient descent towards the optimal value, X star, Y star. Xn, again, is a random variable drawn from the normal distribution with mean of 0 and standard deviations shown here and here. With increasing sigma, convergence of this system becomes increasingly non-uniform. So the green kind of mimics what we see in the black. We have this oscillating behavior around the average, and it converges back down to X star, Y star. But if we were to have noise increase on the order of magnitude, then we get this increasingly non-uniform convergence along the average of the system, and the neighborhood of stability increases substantially. In this presentation, extremum seeking control is introduced as an effective adaptive control strategy when the output from the controlled system can be formulated into a cost function. More specifically, extremum seeking control is an optimization-based technique that tracks local extrema of cost function with the guaranteed convergence and stability under a set of well-defined conditions. This is demonstrated using a motivating example illustrating the structure of the general extremum seeking control feedback loop. In the works of Shanker and Krisick, the authors introduce a novel scheme where the cost function is now confined within the argument of sine and cosine functions. As the main outcomes of their work, they provide guarantees on control effort, as well as stability and convergence proofs about theta star. In application to 2D vehicle control, their claims are effectively demonstrated with the controller modeling unicycle motion, though, as one can see from the results presented, the trajectory developed by the controller oscillates about the average trajectory and is therefore not entirely practical.